Hello my friends and welcome back to the Today Machine channel. The production of heavy-duty springs often employs the hot forming method, where steel rods or bars are first heated to forging temperature, typically between 850 degrees Celsius and 950 degrees Celsius, to achieve maximum ductility. Once the material reaches the required temperature, it is immediately transferred to a winding or coiling machine, where it is hot bent into the desired spring shape. This process allows for precise forming of large diameter or high-strength springs that cannot be cold coiled. The process concludes with dimensional inspection and load testing, ensuring each spring meets stringent specifications for strength, elasticity, and long-term performance. NNN. In the world of steelmaking and rolling mill technology, every movement counts. Power transmission, torque control, and synchronization define product quality and plant reliability. SMS Group's Drive Engineering division is where mechanical precision meets metallurgical expertise. Within the Hilschenbach workshop in Germany, drive systems are engineered from the ground up, designed, machined, and assembled entirely in-house. The production of a large gear unit begins with submerged arc welding under automated control, ensuring perfect fusion of heavy steel components. Once welded, each unit undergoes heat treatment and stress relief annealing to eliminate internal tension, guaranteeing dimensional stability. The gear teeth are precisely milled on CNC gear cutting machines capable of handling diameters up to 6 meters and modules up to 40. After machining, the gears are case-hardened for wear resistance and subjected to ultrasonic testing to detect even microscopic flaws. Grinding on a profile grinder refines the tooth geometry to within microns, followed by 3D laser measurement and computer-aided adjustment of contact patterns. Every housing, bearing, and shaft is manufactured and pre-assembled to achieve seamless torque transfer under extreme loads. SMS Group integrates mechanical design with digital precision. Automated alignment systems and vibration monitoring ensure flawless operation in both new installations and modernization projects. From the first weld to the final torque test, each stage reflects advanced German engineering dedicated to performance, durability, and efficiency. SMS Group's drive technology represents the core of industrial power, precision built for decades of service in the world's most demanding steel plants. Klingelnberg Antriebstechnik operates one of the most advanced large bevel gear production lines in the world, engineered for maximum precision and efficiency. The entire process is built around lean production and lean management principles, supported by the KIMoS software, for precise digital modeling, optimization and simulation of tooth geometry and load distribution. Machining begins with CNC turning and grinding operations, followed by high-precision milling on the world's largest bevel gear cutting machine, the C300, capable of producing gears up to 100 millimeters in diameter. The gears then undergo heat treatment in the in-house hardening plant, providing enhanced toughness and wear resistance through controlled metallurgical processes. Quality control is fully integrated, featuring contact pattern inspection, grinding burn testing, and magnetic particle surface crack detection to guarantee flawless performance. Each component passes a final dimensional and performance verification before dispatch. The modernized bar mill at Hyundai Steel's Pohang plant represents a milestone in advanced hot rolling engineering. Originally designed for rebar production, the facility has been upgraded by SMS Group to produce special bar quality steels with exceptional dimensional precision for the automotive sector. In this high-performance line, billets are heated to rolling temperature and enter a fully automated mill configuration. The existing 14 stands serve as the roughing and intermediate sections, while the newly installed 5-stand precision sizing mill from SMS Group performs the final rolling. Each of the 3 rolls in the PSM completely encloses the material, producing a perfect round cross-section. The PSM features hydraulic roll gap adjustment under load, enabling diameter corrections within milliseconds during operation. Each stand is individually driven through high-torque gearboxes, designed and manufactured by SMS Group. This system ensures stable torque transmission, smooth material flow, and dimensional tolerances up to 10 times more accurate than DIN standards. A fully integrated technological control system monitors every process parameter, from roll pressure to bar temperature, ensuring consistent quality throughout production. The automatic roll change mechanism further reduces downtime, allowing rapid replacement or size adjustments without interrupting output. The result is a seamless high-speed rolling process that delivers SBQ bars from 25 to 83 millimeters in diameter, with superior surface quality, uniform microstructure, and minimal deviation. The modernization demonstrates the technical excellence of SMS Group, merging precision mechanics, hydraulic control, and digital automation to achieve maximum performance in hot rolling technology, not non. The Hosler VRM High 4200 3730 is a 4-roll plate bending machine engineered for universal forming applications. Featuring linear hydraulic movement of the side and bottom rolls, it ensures precise and powerful control during bending operations. This versatile system performs pre-bending of sheet edges, rounding into cylindrical shapes, cone bending, and press bending for both uniform and variable radii. It is also ideal for calibrating welded tubes to minimize radius deviations. The VRM series is widely used for producing tubes, ovals, rounded boxes, and conical sections, making it essential in shipbuilding, pressure vessel, and aerospace manufacturing industries. Alloy steel is a high-performance material obtained by adding elements such as carbon, chromium, nickel, and molybdenum to iron during steelmaking. These alloying elements and controlled heat treatments give the steel superior mechanical properties such as hardness, strength, and wear resistance. Depending on composition and treatment, alloy steels are classified into several groups. Quenched and tempered steels offer high toughness for cranes or wagon wheels. Case-hardening steels provide hard surfaces and tough cores, ideal for gears. Spring steels are elastic and silicon-based, while free-cutting steels allow fast machining. Bearing steels are rich in carbon and chromium for extreme load capacity. Hot work and cold work tool steels resist thermal stress and wear in forging or die applications, while plastic mold steels serve injection molding industries. High-speed steels are used for cutting tools, drills, and precision machining due to their hardness retention at high temperatures. Found in automotive, aerospace, rail, and machinery production, these steels represent the backbone of modern industry. In short, alloy steels are not just materials. They are the foundation of technological progress and industrial civilization. NN. The Davi MCB 4-roll plate bending machine represents a state-of-the-art solution for manufacturing large cylindrical and conical sections used in the wind energy sector, such as tower shells, transition pieces, and foundation rings. Designed for heavy-duty applications, this system provides unmatched precision, repeatability, and automation in handling thick, high-strength steel plates. The rolling process begins with hydraulic pre-bending, where the leading edge of the plate is accurately formed without the need for manual repositioning. The machine's 4-roll configuration ensures full plate control throughout the cycle. The top roll applies bending force, while the lower rolls perform feeding and positioning. Advanced synchronization of hydraulic cylinders allows precise curvature control, ensuring uniform diameter and minimizing flat ends. Equipped with CNC numerical control systems, the MCB machine can automatically manage multiple bending sequences, optimize rolling pressure, and adjust roll movements for consistent geometry across large sections. The rigid frame construction and powerful hydraulic system enable processing of steel plates with thicknesses exceeding 100 mm and widths up to 4 meters. To meet the demanding tolerances of wind tower manufacturing, Davi integrates real-time measurement sensors, automatic calibration, and programmable material compensation. This ensures every rolled section meets international standards for straightness, roundness, and edge alignment, critical for seamless on-site assembly and long-term structural stability. The Heusler VRM 4200, featuring a patented system with upper and side supports, enables precision bending of diameters up to 15 meters with a 150-ton load capacity. Engineered for the most demanding applications, it delivers exceptional performance in producing large offshore wind turbine sections and massive monopile structures with unmatched accuracy and strength. At the Tojiro factory, every knife begins with a block of high-carbon stainless steel, precisely heated and hot forged to form a dense, durable core. The blades are then heat-treated to achieve optimal hardness and flexibility before passing through CNC grinding machines that shape their fine geometry. Skilled craftsmen refine each edge by hand, honing it to razor sharpness. Handles are carefully mounted to ensure perfect balance and comfort. Finally, every knife undergoes strict quality inspection, hardness testing, and polishing before receiving the Tojiro mark, a guarantee of precision, strength, and Japanese craftsmanship at its finest. The production of Tojiro knives, one of Japan's top 5 knife brands, is a fusion of traditional swordsmith craftsmanship and modern metallurgical technology. The process begins with raw steel preparation, where high-carbon stainless steel or layered clad steel is selected for optimal hardness and flexibility. Once the material is ready, it undergoes forging or precision stamping to form the blade blank. In high-end models, the steel is heated to over 1000 degrees C and hammer forged to refine the grain and enhance toughness. The blank is then shaped and ground, correcting any distortion and forming the preliminary bevels along the edge. Next, the blade passes through heat treatment, a critical phase where the steel is hardened and tempered. After heat treatment, the knife undergoes multi-stage grinding and hand polishing, where skilled artisans perfect the surface finish and edge geometry. Finally, each knife is hand-sharpened, inspected, and tested for cutting precision, surface quality, and balance. Through this meticulous combination of forging science and artisanal precision, Tojiro creates blades that embody the excellence of Japanese steelmaking, offering unmatched sharpness, durability, and craftsmanship admired by chefs worldwide. In the heart of Niigata's Tsubame-sanjo region, Tojiro craftsmen continue Japan's centuries-old legacy of blade perfection, where sharpness is not merely performance, but an art form. Just like the katana, Japanese kitchen knives embody harmony between material, structure, and precise edging. The keen edge sharpening process reveals how this balance is achieved through discipline, patience, and skilled craftsmanship. The sharpening journey begins with careful preparation of whetstones, rough, middle, and finishing grades, each chosen according to the blade's condition. After soaking the stones, the craftsman sets the knife at a precise 15 degrees angle and moves it rhythmically across the whetstone. Maintaining the correct angle is essential. A narrow edge enhances sharpness but reduces durability, while a wider edge improves strength but softens the cut. As metal meets stone, a fine slurry appears, an important medium that polishes and refines the edge. During sharpening, the craftsman monitors burr formation, confirming that the blade is reaching optimal thinness. Both sides are ground in a 6:4 ratio, then finished evenly to create balance and long-lasting precision. For traditional single-edged knives like deba or yanagiba, the back is slightly concave to reduce resistance when slicing. The process concludes with kobawase, fine polishing that strengthens the edge and enhances the knife's cutting feel. Tojiro emphasizes that true sharpening cannot be replicated by mechanical sharpeners. Only hand sharpening on a whetstone preserves the knife's geometry, resilience, and signature Japanese sharpness. Through this art, Tojiro not only maintains cutting excellence, but also honors a cultural philosophy to respect, restore, and reuse. A tradition where every stroke of the stone breathes life back into steel. The Model 480B Inertia friction welder is a high-performance 425-ton machine engineered for aerospace component manufacturing. With a maximum speed of 1000 RPM and the ability to weld tubular areas up to 42 inch squared, it delivers exceptional precision and strength. Using rotary friction welding, one part spins rapidly while another remains fixed, generating intense frictional heat. This solid-state bonding process forges titanium and nickel-based alloys into seamless, high-integrity joints, ideal for jet engine components, requiring superior structural reliability. The Hössler FKB plate bending machine is engineered for forming large and heavy plates with high precision. Equipped with a robust 3-roll design, it ensures full-length support of the top roll, allowing tight radii bending even in thick materials. Its key advantage lies in the innovative Bendtronic control software, which transforms manual expertise into a fully digital process. Operators can graphically simulate bending sequences, while the system automatically calculates roll positions, pressure forces, and bending passes. Real-time compensation for springback and material variations guarantees consistent accuracy. Combining mechanical strength with intelligent automation, the FKB achieves superior productivity and quality, making it ideal for manufacturing components used in shipbuilding, wind energy, and heavy steel structures. Friction welding is one of the most advanced and precise technologies used in the modern automotive industry, playing a crucial role in the production of high-strength, lightweight components. Unlike conventional fusion welding, this process does not require melting the materials. Instead, it relies on heat generated by mechanical friction between two surfaces, followed by a forging pressure that permanently bonds them together at a molecular level. The result is a solid-state joint with exceptional strength, integrity, and dimensional accuracy. In shaft manufacturing, such as for drive shafts, axles, and steering columns, friction welding offers outstanding reliability. The process begins with one part rotating at high speed while being pressed against a stationary component. The frictional heat softens the metal surfaces, and once the rotation stops, an axial forging force is applied to complete the weld. This produces a seamless joint, free of impurities or porosity, ensuring uniform material properties throughout. Modern friction welding systems are fully automated and equipped with CNC-based control units that monitor parameters such as rotation speed, friction time, forging pressure, and temperature. These precise controls enable repeatability and ensure each weld meets the stringent standards of the automotive industry. Non-destructive testing methods, including ultrasonic and X-ray inspection, are used to verify weld integrity before final assembly. This technology is particularly effective for joining dissimilar metals, for example, aluminum to steel, allowing automakers to optimize weight reduction without compromising structural strength. Additionally, friction welding consumes less energy than traditional arc or resistance welding and produces no harmful fumes, making it a more sustainable manufacturing solution. From engine components to suspension systems, friction welding enables the production of parts that deliver higher performance, greater durability, and enhanced safety. By integrating this technology, automotive manufacturers achieve precision engineering, improved fuel efficiency, and a significant step toward greener, more efficient vehicle production. The Davi MCP angle roll 3-roll system demonstrates exceptional versatility in bending complex profiles. In this operation, it forms a spiral shape from 4 welded tubes, showcasing the machine's precision and power. The synchronized 3-roll design provides consistent pressure and accurate curvature control, even in multi-tube configurations. This advanced process highlights the MCP's capability to handle custom structural applications, making it ideal for architectural, industrial, and heavy fabrication projects requiring high-precision spiral or helical bending. The 40mm steel ball production line operates through a high-output, fully automated process. Heated steel rods are cut, forged, and rolled into spherical shapes using precision dies. The balls are then heat-treated, quenched, and tempered to achieve uniform hardness and durability, followed by grinding and polishing, ensuring perfect roundness for industrial and bearing applications. The automated train wheel production process represents one of the most advanced examples of industrial forging technology. It begins with the loading manipulator, which precisely positions the heated steel blank into the blanking press. Using an exact centering system, the blank undergoes upsetting under a 9,000-ton press force, forming the initial wheel profile known as the wheel blank. Once the primary shaping is complete, the blank is removed by a transfer manipulator, initiating a fully automated sequence involving 3 industrial robots that handle cooling, lubrication, and CNC-controlled axis adjustment. During the rolling stage, the wheel blank is formed without a mandrel, guided only by web rolls, a pressure roller, and lateral rolls to achieve precise geometry and density. Real-time tool setting corrections can be made during rolling to optimize material flow and accuracy. Subsequent steps include automatic die cooling and lubrication, followed by needle embossing for permanent wheel identification. The oscillating needle system ensures high-precision marking without compromising material integrity. Each finished wheel is transferred to a 3D laser measuring machine, where dimensional accuracy and surface quality are inspected. The integrated automation and traceability system monitors, documents, and archives every production stage. Controlled by Rolltech wheel technology software, the line produces up to 280,000 wheels per year, with diameters ranging from 700 to 350 millimeters, ensuring exceptional quality, consistency, and performance for modern rail applications. NNN. The extrusion operation starts as high-quality PVC material is delivered to the mixing hopper, where stabilizers, colorants, and performance additives are precisely blended. The compound is then fed into a twin-screw extrusion machine, where temperature and pressure are carefully controlled to make the material soft, uniform, and ready for shaping. Next, the softened PVC is forced through a precision-engineered die, forming the multi-chambered aluplast window profiles. Immediately after extrusion, the profiles pass through calibration and cooling tanks, where water or air rapidly stabilizes the shape and ensures dimensional accuracy. Once cooled, an automated puller and cutting system slices the profiles to the required lengths, and the surfaces are checked for flatness, straightness, and finish quality. Every batch meets strict standards for thermal insulation, acoustic performance, and weather resistance, core principles of aluplast products. The entire extrusion line is monitored by a central control system, collecting real-time data on temperature, pressure, and line speed to ensure consistency and quality. The Bailey RDB 175 hydraulic tube bender precisely bends stainless steel tubes, such as 28.5 times 1.5 mm, to a 100 mm centerline radius. Equipped with a digital controller, the machine stops automatically at the set bend angle, replacing the former analog system. It handles up to 2.5 mild steel, 60 mm stainless steel, 2 square tube, and 1.25 solid steel bar.